This time, we are to determine the subgroups of Z8 under addition modulo 8. So our set is identified as a set containing the elements 0, 1, 2, 3, 4, 5, 6, and then 7. In a previous video, already declared that this is actually group under the given operation addition modulo 8. The task for this video is to identify the subgroups intended for this given group. Take note that the subgroups are also grouped in their own nature, but they correspondingly contain the identity element of the original set or the given set and the corresponding inverses for each of the elements therein. Now, to identify, take note that we have here 8 elements, and if you're going to talk about subgroup, they are also subsets, and if you would like to take the number of subsets, that's 2 to the n, that's 2 to the power of 8, that's actually very large. That's actually, if I'm correct, that's 256, right? Hence, you have 256 subsets to try and determine whether they are actually grouped. But of course, we have different conditions and axioms for a certain subgroup or subset to be a subgroup. At the same time, let us use the idea of the Lagrange theorem, because the Lagrange theorem will actually trim down the process in determining the possible subgroups of a given group. The Lagrange theorem tells us that the order of our given group, in this case 8, order means cardinality as well, the order of the subgroups intended as H or represented by H are actually equal to the common, the divisors or the factors, integral divisors of the order of the set 8. The factors here are actually 1, 2, 4, and 8. And what does this tell us? This tells us that out of 256, it's easier for us to trim down the items because we are guaranteed by Lagrange theorem that the order of the subgroups that we need to identify are only with 1, 2, 4, and 8. This also tells us that there is no possibility for a certain subset with 3 elements, 5 elements, 6 elements, and even 7 elements to appear for this. So actually, the number of possibilities that from 256 is now even smaller. And at the same time, we will be applying the considerations for a certain subset to be called subgroup. So here comes the process. Let's try to determine first the given what they call this one, first subgroup, the subgroup with order 8. The first subgroup is actually the group itself, the group containing 0, 1, 2, 3, 4, 5, 6, and 7. This is the subgroup with order 8, and the subgroup, the group is also a subgroup in itself. So we are now okay with the subgroup with order 8. Okay, that's already okay. And the second one is, of course, the subgroup containing the identity. This corresponds to the subgroup with order 1. So looking at our k-list table presented here, also provided in one of the videos discussing the or verification of the given set to be a group under the given operation, and we had that in this playlist. Let's try to make some time in reviewing that. This KD table is also there, will help us identify the identity element for this group, because the identity element for the said subgroup should also be the same identity element for the group, because the identity element is unique for a certain set or group. Okay, and since subgroups are just subset of the given group, it also contains the same identity element. Now, how do we determine the identity element here? Simply look at the column and rows having the same inputs, talking about this and that, because these are the values with the same results as the elements being implemented. I'm talking about first here when we have 0 operated by 0, so the result is 0. 1 operated by 0 is just 1. 2 star 0 is 2. 3 star 0 is 3, and you can see the rest of the items here are just actually in itself as presented by the items here. At the same time, if we're going to have 0 operated by 1, it's just 1. 0 star 2 is 2, star 3 is 3. So basically, we have guaranteed here that our identity element is actually equal to 0. So our second subgroup, meaning the subgroup with order 1, is actually the subgroup containing the identity element. So it's actually equal to the set containing is 0. Okay, so we have now the two subgroups identified for this item. Now, the next task here is to identify the non-trivial or the proper subgroups. We are now going to proceed with the subgroups with 2 and so on and so forth number of elements. As mentioned in the language theorem, there is a possibility for us to identify a subgroup with 2 elements, but we don't need to try 3 because 3 is not a divisor of 8. So we'll jump into 4 and that's it. We don't need to try 6, 5, and 7. So for the order of 2, take note that the idea for subgroup, okay, a subgroup should contain, or there should be an existence of identity element. The identity element is actually 0, so for every pair, that means because we're talking about order 2, for every pair, 0 must be contained in that. So the possible items or sets to be checked or verified whether there are subgroups are actually 0 and 1. We don't need to start with 0, 0 because set is just allowing us to write no duplication, so it's just the same as that. So we don't need to write 0 and 0. So we'll start with 0, 1, then 0, 2, then 0, 3, followed with 0, 4, 0, 5, 0, 6, and 0, 7. Okay? But not all of these 7 are actually subgroups. We just need to identify the next part or intended item for our subgroup. There should also be the existence of inverse elements for every element in the given set to be called as a subgroup. Now, take note that we can also find here, let me erase some scribbles here. Okay, hopefully I could erase the black one. So I'm going to I'm going to write again those items that were removed by this. Okay, so let me rewrite here 1. Okay, just like that. For the existence of inverse, it's actually the value when operated with, or element rather, when operated by another element would result to our identity. Take note that our identity here is actually 0. So for the grids containing 0, this will tell us the inverses of every corresponding element. Talking about here, 0 star 0 is equal to 0. That would mean that the inverse of 0 is just 0. Okay? Now for 1 star 7 will result to 0, hence the inverse of 1 is 7. Then the inverse of 2 star 6. Okay, so 2 is 6. The inverse of 2 is 6. How about the 3? For 3, it's actually 5 here, so you have the inverse of 3 is 5. How about 4? The inverse of 4 star 4, you will get your identity element of 0. So the inverse of 4 is 4. Next, the inverse of 5 star 3, you will get here 0, the identity element. So the inverse of 5 is 3. Then the inverse of 6 is this one here, is 2. And finally, the inverse of 7 is 1. So these are the following corresponding inverses: 0 for 0, 7 for 1, 2 for 6, 5 for 3, 4 for 4, 3 for 5, 2 for 6, and 1 for 7. The point here is that when you look at these pairs of elements already containing the identity 0, we also need to identify or determine whether the inverses are already also found here. If the inverses are already found there, we're also going to check the last portion, which is closure property, to determine the subgroup. Now take note of the first one. The inverse of 0 is 0, but the inverse of 1 is 7. Since 7 is not there, we're going to drop that. Basically, it's no longer a subgroup because 7 is not part of the given pair of elements in that set. In short, the inverse is not available for 1. Hence, remove that because for it to be called a group, inverses should be present. As for 2, 0 is the inverse of 0 is 0, but the inverse of 2 is actually 6. So again, we'll drop this. Next, the inverse of 0 is 0, but the inverse of 3 is 5. Similarly, drop that. How about 0 and 4? The inverse of 0 is 0. The inverse of 4 is also 4. So how about this one? Do we consider this as a subgroup? The next part here and the last part is the identification of closure property. The closure property tells us that when we are going to operate the elements inside to itself and to the other one, let's say here 0 star 0, 4 star 4, and 0 star 4, will the resulting values here still be part of that? And if it's yes, then we can consider that a subgroup now because it contains the identity element, the inverses elements of both, and if this would be satisfied. Going back to our kitty table, 0 star 0 is 0, so it's already okay. 4 star 4 is also 0, and 0 is still there. And 0 star 4 is actually 4. Even 4 star 0 is also 4. With all of this, still element of that, again, identity element is there, inverse is already there, and it's already closed, then this is, of course, obviously, the third subgroup after this 2 here. Since we're not yet done, let's continue. For 0 and 5, 5, its inverse is 3, not there. Drop that. 0 and 6, the inverse of 6 is actually 2, not there, so drop that. 0 and 7, the inverse of 7, okay, is actually 1 and it's not there, you drop that. In short, we only have one subgroup of order 2. Okay? So that's already okay. The next step now is for order of 3. Okay? Let me label this. IV. Order of 3. This was earlier order of 2. However, for order of 3, since according to the language theorem, there's no possibility for 3, the next step is 4, and actually the last step is 4. Therefore, let's not anymore solve for order of 3. This is why it's very nice to really apply the language theorem for finite groups since the given set is a finite. So let's end with order 4. Now, looking into this, there are a lot of combinations for 4. Take note, there are 8 elements, and considering that, say for example, 0 as the identity element should be always there, there's still a lot of possibilities in selecting 3. Okay, 3 or more. So my suggestion here is look at the order of 2. Those which were dropped down, let's try to complete them and look for possibility of order of 4. Let's talk about 0 and 1. Okay, so let's have 0 and 1. We know earlier that this is not a subgroup because it lacks something else. So what it lacks is actually for 1, when its order, its inverse is 7. So 7, its inverse is 1, so it's rather okay there. However, we need to add another item for it to be considered as order 4. At the same time, if we're going to operate using closure property, how about 0 star 1, 0 star 7, 1 star 7, 1 star 1, 7 star 7? Would this be closed? Because if we're going to have 0 star 1, obviously that's 0. This is also 7, so they're already there. 1 star 7, actually here, 1 star 7 is still 0. Okay, that's okay. So 1 star 7 is 0. But 1 star 1 is actually 2. Right? So we need to add 2 here. But then again, the inverse of 2, going back to inverse, is 6. Right? and then later on we would see that it's no longer order of 4. So basically for 0 and 1, it's no longer possible. We drop that. How about 0 and 2? Okay, so 0 and 2, and simply add the additional what do you call this one, inverses. Take note, 6 should be there, should be part of that component, so we just need one more. But then again, if we're going to have 2 star 2 for closure property, 2 star 2 is actually 2 star 2 is 4, right? So we are going to add here 4. Okay, so it's 4, so that it will be closed. Now how about 6 star 6? 6 star 6 is actually 4 as well. So more or less we're going there. How about 4 star 4, the newly added element? 4 star 4 is actually 0. Okay, so 0. So how about this one? Do we consider this now? Let's try to look for other. 2 star 6, 2 star 4, 6 star 4. 2 star 6, this is now on the closure property. 2 star 6, sorry, is 0, okay. 2 star 4 is 6, okay. 4 star 6 is also 2. So basically, 2 star 6, okay, was actually 2. This was 6. Sorry, this is 0 rather. This is actually 6, 2, right? So basically, they are still there. It's possible. So what you can see here is this is another subgroup where it is actually closed now. It contains the identity element and the inverses of each. The inverse of 2 is 6. The inverse of 6 is 2. The inverse of 4 is still 4, right? Okay. And then when we're going to pair this, 6 and 4, 2 is already there. It's closed. 2 and 6 is 0. It's there. 2 and 4 is 6. It's there. 6 and 6 in itself, 4. 4 and 4 is 0. 0 and 2 and 2 is 4. So they are also closed. So this is already okay. Okay. Now, we are not yet done because we still have 0, 3, 0, 5, 0, 6, and 0, 7. Let me add another page here if it's okay with you. Okay, so let me add other page here. Now, I'm talking about the idea of adding 0, 3, and then later on 0, 5, then 0, 6. But this was actually during the order of 2. In short, we're going to add something here. For 0, 3, take note that here earlier, the inverse of 3 is 5. So that means 5 should be part here, so that inverse should be included. But when we operate 3 star 3 and 5 star 5 in our KD table, 3 star 3, okay, 3, sorry, let me use black. 3 star 3 is 6. 5 star 5 is 2. So we need 2 and 6 for this one here. So when we need 2 and 6, this is no longer order of 4. In short, this is no longer possible. Similarly, if we have here 5, yeah, take note this is 5, right? Okay, this was 5. So it should also contain 3 because the inverse of 5 is 3. Okay? So the inverse of 5 is 3. But basically, you will repeat this pattern here and would include 0, 2, and other, sorry, 6 and 2, and other things if there are still possibility. So we drop down this possibility. How about 0 and 6? The inverse of 6, we know this already. The inverse of 6 is actually 2. Okay? So we add here 2. But if we have 6 star 6 and 2 star 2, you will actually get, okay, 6 star 6 in the KD table. 6 star 6 is 4. And then 2 star 2 is also 4. So we will actually be adding 4. But take note, this is already identified previously here. This one, 0, 2, 6, and 4, we are just rearranging it differently. So they are just the same. So we don't need to rewrite that. They are just the same because we're talking about sets and subgroup. And that's already okay, but we already identified that earlier. The final remaining pair that we have dropped earlier on order of 2 is 0 and 7. But similarly, the inverse of 7 is 1. Okay? So just like this one here, 7 and 1 are here. So 7 and 1. But we have 7 star 7 and 1 star 1. You will get 7 star 7 is 6 and 1 star 1 is 2. So you will be adding here 2 and 6. Still drop that because it's no longer order of 4. So in short, for order of 4, our subgroup is 0, 2, 4, and 6. Similar to that, just simply written differently. So this is our subgroup in order 4. Take note that the Lagrange theorem allows us to stop at 4. We already have our 1, 2, 4, and 8, and that's already okay. So to finalize here, just for the final statement here, the subgroup of Z8 under addition modulo 8 are the following. First, you will have the set itself 0, 1, 2, 3, 4, 5, 6, and 7. This is actually with order 8. Next is a set containing the identity element. This is actually of order 1. Next, for our order 2 or order of 2, it's actually 0 and 4. So 0 and 4. And you have 0, 2, 4, and 6 for your order 4 or order of 4. These are the 4 subgroups of the given group presented here. So it's a little bit longer because we are trying to examine the conditions that should be met. But of course, as we move further the topic in groups and subgroups, there might be some shortcuts or other methods that will actually help us identifying the subgroups in more efficient and a faster way. Just for this given, we will have 4 subgroups. Thank you very much for watching.